Okay, in this video I'm going to show you how to do gyro-orbit heat flux predictions in heat. So I guess I'll start by saying there is a paper out there. It's linked on the GitHub page that describes the algorithms I'm about to go into. It's published under open access, so you should be able to access it no matter what your affiliation, and it's in the Nuclear Fusion Journal. So that's a good starting point to just sort of figure out what we're talking about here. And I go through the sort of the mathematical derivation of the gyro-orbit, all the functions. And there's an image in here that I wanted to show to start with here. So this green line you're seeing is the trajectory an ion will follow around the magnetic field line due to its cyclotron motion. So if you have a larger energy, you'll probably have a larger radius. And as you can see, like if we assume particles follow this yellow line, which is actually sort of true for electrons because their Larmor radii are so tiny, they basically follow this yellow line. If you just assume that all the power flows along this yellow line, like in this example, we would not strike any surface coming down this toroidally running gap. But if you include the helical trajectories, you can see we're loading this edge. So it's important because when you turn that feature on, you'll end up, I think there's some images down here. Is it down or is it above? Yeah. You'll end up loading regions which were formerly shadowed. So on the left here, you're seeing the optical approximation. So this is assuming power flows directly along the magnetic field line. This is a single castellation in the diverter of NSTXU, and you can go look at this later, the paper, but this is a shadow that only appears if you assume power flows along the magnetic field line. If you start including the helical trajectories, you get this sort of a smearing in of the shadow. You also get this very hot corner right here, and that is because particles can loop around like I'm showing in that plot above and load that corner. So not only are they loading this side, but they're loading this corner, which is that corner that we're showing. So it's important to include these trajectories if we're trying to get the most accurate physics representation. Now, the one disclaimer that I'll say right now is that there are no electric fields included in this. This paper talks about why we're doing that and some of the assumptions that went into that, so look into that if you're curious. So I guess what we'll do is we'll start with now that we have a sort of idea of what we're after, I'm going to show you how to do that. So in the releases page of heat, you can get this test case. That's 3.0.zip is the latest one. I might come out with a later one, so just get the latest one. And then inside of that folder, you should have a good, let me find that folder. You'll have a batch file and then this NSTX folder. The batch file is just for terminal runs. This movie is about using the graphical user interface. But if you know how to use the terminal, the same, everything I described here would port over. So there's some GQ disks in this file. There's a gyro-orbit trace file, which is just for if you wanted to like make a visualization of, for example, like one of these helical traces. That's what that gyro-orbit trace file is for. There's an input file. There's a PFC file. This file we won't use. It's a rad power file for radiated power module and heat. And then there's a CAD file. So let's start by looking at the CAD file. So what we're trying to do here is calculate the heat flux onto this middle tile from the gyro-orbit algorithm. This middle tile is called solid 843. In order to do that, you need to include flux tubes that are outside of this tile, right? Because I might have a flux tube, let me turn that off, let me turn everything else off. I might have a flux tube that's out here, like it's coming from right to left and it's going like this, but the Larmor radius is large enough that it can strike this surface. So if I only use this tile when I'm trying to define all the flux tubes I want to trace, I'll miss some. I need actually a footprint that's wider than this tile at a minimum in flux space by the minimum or the maximum gyro orbit size, the gyro radius size in flux space. So like if your maximum gyro orbit size is your gyro radius size is a few millimeters, then you need to like be a few millimeters out from this edge. And so we have a plane that I've included in this file, which does that. And because, you know, the field lines are in this particular magnetic configuration coming from right to left and going down, I've also oriented it over here. So you can do traces from all the corners and then just like basically build a gyro source plane by expanding where those traces intersect. It's sort of a little bit of a black magic, like you just tune it till you figure it out. But you'll need to have a gyro source plane if you really want to accurately capture the heat flux. So these are the two components we really need, and then all this other CAD is just stuff to help make the correct shadows. So we have the upstream and downstream CAD tiles, and then we also have this plane, which is just sort of representing a carrier that this tile would sit on. So if we now go to our PFC file, so this is our PFC CSV file. When it comes from you, actually, it will look like that, where you have this this line, example for optical calculations in red, power calculations, is uncommented. We want to comment that, and we're going to uncomment this. So this 52 through 54 here in this example is for gyro orbit calculations. And so we need to calculate the solid 843 power, and then we also need to calculate this gyro source plane power. And the reason is how it's going to work is we are going to trace power from basically up at the plasma core. We're going to trace down and map all the power down onto this surface. This is the gyro orbit source plane, or the gyro source plane is what it's called. And then once we have the optical power mapped around here, which we can validate power balance on, right? We can weight the amount of power that goes into this by its fractional component of the toroidal, of the full toroidal machine, and basically achieve power balance numerically. Then we'll take all of those mesh triangles all over this surface that have the optical power, and we'll split that power up from each mesh triangle and send it down in helical trajectories onto the target, which is this 843. And there's an image in my PhD dissertation which sort of shows that this, where we have, you know, for this example, we're doing a trace down from the gyro source plane towards this PFC in the region of interest. And it'll intersect somewhere, and that's where the power will be. So we're basically taking, it's a transfer function that takes the optical power assigned on this plane at each flux tube and splits that power and then maps it down to this this PFC. And that function is described in this paper. I can show that. There's a discrete and an integral version of the function. Sorry, it's taking so long to scroll up here. Just for the record, this is a typo, should be a X. But so the power at some point y on the target is the integral over several different distribution functions that give us our fractions. And we're just taking the optical approximation power on the target, on the gyro source plane, sorry, and then we're mapping it down, and this function is a mapping function. So it's a Dirac function that only is one if the helical trajectory that originates at some flux tube on the gyro source plane lands on the target. So you can go more into the paper there, but basically we're mapping power from this to this. So we need both. And then the other thing to note is we're also calculating the optical power in this calculation. So we want to exclude this gyro source plane from the optical power calculation for 843. Otherwise, it would cast just this huge magnetic shadow down. So that's why we have in the these lines, we're excluding gyro source plane from the calculation for solid 843, and then we are running it on a separate line. We're running an optical calculation for this, and then it's including everything. So that's the PFC file. We'll save that. The input file, there's some iron gyro orbit heat flux variables, but we'll go through those in the GUI. And we can actually, I didn't know that was in there, so that can actually be turned off. So we can just, all we need in here is gyro source plane. There's only one CAD object that we are using as a gyro source. So yeah, so we have that, and I think we were good to start. So we can go over to the heat GUI. I'm going to refresh it just so everything's good. By the way, you can change the theme in this now. Sort of like Cyborg. And we're going to select the machine. It's NSTX. We're going to select our, G file, which it could be any of these. They're all the same, or sorry, input file is what we're doing right now. So we're going to do NSTX input. So it loaded them, great. And then we're going to go to the MHD settings. We're going to make sure our shot number matches our, I'm just going to close this. We're going to make sure that our shot number matches our GQ disk shot number, and then we're going to pick any one of these. It doesn't really matter. So we're doing 50 for this one. I'm going to load that, and then I'm going to load the MHD. And we can see that the region we're talking about here is right down here on this flat tile. Then we're going to come into the CAD settings. We're just going to do standard for our intersects, and then we're going to load our CAD file. Now that the CAD file is loaded, we can do the PFC file. That's the one we just edited. So again, we have our solid 843 excluding gyro source plane, or else it'll cast a non-physical shadow, and then we're actually also calculating gyro source plane. We're going to load those settings, so it just meshed those objects. And then I'm going to come into the optical settings. I'm just going to use the defaults here. So we're using IX regression 15 for lambda Q, 10 megawatts of injected power. We'll load that. And then we're going to come to the gyro settings. And so there's a lot of variables here, and I'm going to sort of go through what they are. So this number of steps per helix is the number of discrete straight lines that we're representing each period of the gyro-orbit helical trajectory with. So if we go back to this image, this curved helical trajectory is actually a discrete trajectory, just like the magnetic field line is. And each one of the periods, so like from here to here, is discretized in n number of steps, and n is this number. So I'm saying I'm going to discretize each period by 8 flat line segments. Here I'm going to say the gyro phase angles, so I'm going to put in 3 here. The gyro phase angles, if I look, I'm just going to load these right now. I'll actually just, yeah, we'll just do this for now. Load gyro source settings. You can see over here, if I go down to these plots, the gyro phase angle. So this is like the start angle of the particle. So if this is the guiding center, where around the guiding center in the perpendicular plane to the magnetic field line are we starting? And if we do 3 samples, you can see we're discretizing this full space into 3 different samples. If we go and we change that to be, 6, and then I load the settings, I can see over here that there's now 6 different samples sampled in the perpendicular plane. So this is a spatial distribution function telling us like how many different locations are we going to launch particles from about the guiding center. So go back to the inputs. I'm going to change this back to 3. The trace length is just like the magnetic field line trace length. How far from the gyro source plane do we want to trace? So like from here going forward, how far do we want to trace? So 10 degrees will be fine for this example. You can change the ion mass. This is just deuterium. There's only one option. Maybe eventually we'll add this in. So I think if you do this, it says, yeah, you can't do it yet. So it's just single value. This is basically saying, how do we want to define the velocity? And so what we're going to do is we're going to describe an average temperature over the entire PFC surface. So I'm just going to say 100 eV, which is probably too high for NSTXU, but it'll create larger gyro orbits. Well, we'll change it. We'll do actually 50 eV. And then we're going to do the number of velocity slices. So I'll start with this, and then the number of velocity phases, 3. So I'm going to start with 3 and 3 for both of those and just load them to show you what I'm talking about. If we come over to the output tab, you can see this is the velocity phase angle. So number of velocity phases. And we have 3 different samples put in here. This is a polar plot. Basically, it's V parallel, and then this actually is cut off, but it should say V perp down here. So this is the sharing between the perpendicular and parallel components of velocity. So the total velocity, I think I have this in the paper, will be shared between perpendicular and parallel components, right? And the relationship here is here between V. So this beta angle is what we are defining in our velocity phase. So we're just basically saying if you're here, it's pretty much V perp. There's a little bit of V parallel. If you're here, it's pretty much all V perp, just a little bit of, sorry, if you're here, it's all V parallel, a little bit of V perp. And so this will change the size of the helix. So if you have a higher V perp component, then you will have a larger gyro radius, smaller helical distance traveled per period, right? And the inverse is true over here. So you want to sample through this to get a bunch of different shapes of helixes. And then the other thing that we selected here was the velocity slices. This is basically the slices we're taking from the distribution function. So this is a Maxwellian distribution function. So we're sort of taking the assumption that far upstream from the PFC, the distribution is Maxwellian, and we're just carrying that down. We could, in the future, modify this distribution function. But for now, what we're doing is we take this distribution function, this Maxwellian, and we calculate the CDF, which is this plot on the bottom. And then, so each one of these, for this example, has 33% of the total integrated velocity under it. So each one of these points is placed uniformly within the CDF. And so these CDF bounds that you're seeing here are overlaid onto the plot here, and these are the points, 1, 2, 3, right? So these are evenly spaced in velocity space so that they are weighted to be uniform, right? So it's a uniform weight in the CDF. So if we change, like, for example, to be like, let's do 7, well, not 37, that'll be hard to visualize, and I don't know, 5 for the velocity phases. Let's load those, and we can see over here we now have 7, 1, 2, 3, 4, 5, 6, 7 slices from the distribution function. So this will be a really fast particle, this will be a slow one, and then even if you choose a fast one, it still will be now discretized this number of times, right? So when you do, like for this example, we have 3 heat gyro phase angles, and then we have 5 velocity phase angles, and then we have 7 of these velocity distributions. So this would be the total number of macroparticles we're going to trace from every mesh element center, right? So every one of these corresponds to a different helical trajectory, right, from a single mesh element center. So if we did 3, 5, and 7, you know, that's what, 105? It's 3 times 5 times 7 macroparticles. And so you are going to trace from each mesh element on the gyro source plane 105 or whatever it is, 3 times 5 times 7 macroparticles down to this target. So if you had 100 different mesh elements on this plane, you'd be doing 100 times 3 times 5 times 7 different helical trajectory traces down to the plane. And the power that goes to each particle is weighted by these distribution functions here. So like this one is obviously just uniformly split. This one is uniformly split in spherical coordinates. And then this one is split based on the PDF energy or the sample energy. So that's all described in the paper. But basically, we've now sort of constrained we've defined the number of macroparticles we want. I usually start at a low number and then increase. And for this example, I'm just going to do 3, 1, and 1, just because I want this to run fast so that it doesn't take long for this video. But usually you want to go, like, I would say is you want to start with like 3, 3, 3 or something. And I've run up to like 12, 12, 12, 15, 15, 15 before. It can be computationally expensive, so it can take on the order of hours, maybe into days if you have a super big mesh. So start with something small and then see how long it takes. Make sure that your inputs are set up and then run it overnight or something. So the other thing that we need to define here is the gyro-orbit power source. And this is important. So if you choose all ROI PFCs, it's just going to launch field lines from each PFC and then trace it back to itself. And that's not very good. I should probably remove it, but it's a legacy feature. The better way to do it is to say user selected PFCs, and I'm going to say the gyro source plane is the power source. That's what I'm saying here. So if we go back to this image, this is where the gyro orbit source is the power is gonna be defined, and then we're gonna trace from there to all the other objects in CAD. So I don't want to include solid 843 in this. I only want to include the solid gyro source plane. So I'm gonna load that. Come over to output. We see we have 3, 1, and 1. You'll note that this is a little off, and that's because this distribution function, is truncated. And we can see here gyro source plane is our source for gyro orbit power is gyro source plane. So we're all good. All of our other inputs are set up, right? We got our optical heat flux settings. We have our gyro orbit settings. So we're good to run. So we're just going to do a heat flux point cloud, and then we're also going to do ion gyro orbit heat flux point cloud. And we'll leave all of that on. You could change this if you only want a mesh file or whatever, but we'll run that, and then I'll pause the video and I'll come back with the results. And actually I'll let you see here that the terminal, this is the optical calculation. It'll be done pretty quick. It just did solid 843, now it's doing the plane. Done. And so now we're doing the gyro orbit calculation. So you'll see it's walking through gyro phase angle. You can see that gyro phase, velocity slice correspond to all those samples that I talked about before. So this is sample 000. We'll do our 10 steps or whatever, and then we will. It's actually going to be more than 10 steps because we defined in our MHD settings we're doing quarter degree toroidal steps for 10 degrees. So that means there'll be 40 steps for each macro particle, and you can change that if you think for very shallow field lines you want to make that step size very small. And you can see it goes faster as it gets to the end because there's less particles to trace, and it's intelligently filtering out the particles. So now we're on gyro phase 1, and so this one will go probably pretty quick. I guess I won't pause the video. And then the last, I think there's only 3 in this because we did 3 gyro phase 1 and 1. So this will just be 1 particle, but this is only for 1 CAD. So I will pause it and I'll start when this finishes. Okay, so this just finished. The heat run is complete. We can see in the terminal it finished out. We can see that for the tallies we had some power here. And you can see here the optical power and then the gyro power. They're pretty close. In the limit that you are increasing the number of macro particles, they should align if the magnetic field is not strongly varying across the PFC. So here they're a little bit off, but we only did 3 macro particles because we did 3 gyro phase angles and 1 sample from the Maxwellian and 1 sample in the velocity phase space. So this won't be super accurate, but you can see it is pretty close given that. It was only for 3 macro particles, and we're discretizing all of the entire velocity space with with a single particle. So we're going to open some of those. So in this folder, NSTX. So if we go to the heat/data folder, go to your NSTX, we did 50, I think was the time step we did. And there's this intersect record. These are files that have the actual, the location in the mesh where each particle intersected. So it will be of length. The length of this file, of the number of rows, is the number of gyro source plane mesh elements, and in each row there is a index that corresponds to the element on the target that was intersected. And you can see it's 0, 0, 0, 1, 1, 1, 2, 1, 0, 0, 2, 0, 0. That is the gyro phase angle, velocity phase angle, velocity slice. So for every macro particle, there is a file written that tells you exactly how the intersections happened. We also have the CSV files, the standard heat CSV files. We're going to go into solid 843, and then we're going to go into the ParaView folder, and we're going to open the first the optical. I'm just going to do the meshes. So here's the mesh. So there's the optical mesh that we're all probably pretty used to, and then let's open the gyro-orbit mesh. So we can see that it's a little bit of like a fuzzy version of the optical mesh, right? And so this is sort of what we'd expect. I have in the paper an example of if you increase the number of gyro phase angles. We go down to the very end of the paper, there is a comparison for 3 different, so this is the optical, this is 10 eV for the ion temperature, average temperature, and this is 100. So as you increase the temperature, we smear into the shadows more. So this looks reasonable for, you know, the 3 samples. It's a pretty coarse mesh. This isn't a very fine mesh. As you can see, it's very choppy. Only 3 macro particles. This is pretty good. So this just shows you how to run the gyro-orbit algorithm. So feel free to port this over to whatever workflow you want. I don't think there's much else to say. I think there's some other files in here, like there's a shadow mask for the gyro orbits, there's a shadow mask for the optical. If you do go into like the all folder, so this is at the top root of the time step, the ParaView folder, if you open that and we opened that mesh, it'll also show the plane, right? Which we don't want because this plane doesn't have any gyro source power because we traced away from it. So you want to go into the individual PFC folder in order to get the gyro orbit fluxes. And you can even see actually in this, look at that. There's some weird edge loading things happening, and some edges I can see down in there, in that gap. There actually a particle or two maybe made it down in there. And if we looked at the point cloud, that might also be a little more useful. If we look at this point cloud file and apply that, turn off these meshes, and then turn on the CAD, we maybe be able to like look. Oh, that was the all. Sorry, we don't want the all. We want the one for solid 843. That point cloud. Oops, that was all again, or that was the optical. We want the gyro point cloud. Sorry. Okay, so if we look in there, we could probably see those points in the gaps. That, yeah, you can see how there's some loading in there. Let me make it a better view here. And then let's change our points to be bigger. And you can see some of these particles escape down in there, even with their with only a single sample from the gyro phase space. They made it down and loaded that stuff. So, anyways, that is the heat gyro orbit algorithm, and yeah, I hope that this video was useful. If you have any questions, look to the paper. You could also email me. My email is on GitHub, or if there's a problem with the code, please submit an issue report on GitHub. Anyways, thank you.